Hey folks, and welcome to the lectures on mountains and geologic structures. I am, in fact, going to break this down into geologic structures and then mountains. It just seems to work better that way. Your book or textbook lumps everything together, but this will give you a lot more detail, I think, the way we're going to present it. It will be pretty long, and this is the same way it occurs in class. I think the lectures in class usually go about an hour and a half long, 2 days of 45 minutes, but in class at least you can do questions and answers. You are welcome to raise your hand here, but I'm not sure that's going to do a whole lot of good. And you know what? This is going to sound a whole lot better, I think, if I put my headphones on first. Just for the heck of it, I wanted to show you these pictures. This is from Rondônia, Brazil. In the left column, that's an aerial photograph from 1975. Here's 1989 and 2001. We are quickly removing the rainforest. Bad in many ways. 1, the trees are gone. 2, the soil erodes. 3, the rain goes away. Why? A good source of the rain, if you remember, comes from transpiration from trees that goes into the air and then recondenses. You're essentially creating a desert out of an area that was a rainforest. But hey, it's all about profits. Again, this is a geologic map of Arizona. I just love looking at this kind of thing. And I also like this kind of thing. Take a look. There are all kinds of structures here, but all these guys are horizontal, like the law of original horizontality. Are rocks always that way? Uh-oh. Nope. And no, this is not the effect of a weird lens. The landscape really is bent this way. This is the Colorado River going through Canyonlands National Park. And this is a strange uplift. If you ever get up there, you'll see this. Take a look at these rocks, which probably were at one time horizontal. Something has happened to them. Now imagine if you took a bunch of sheets of paper, stacked them on top of a table. What could you do to get sheets of paper to do this? The obvious answer is crunch them together. And that's what happens with the Earth. And sometimes things are just uplifted. At least when we look at part of it. There's probably more going on to this than what we see in the picture, but that's enough for now. And this is just crazy. We have here some folding going on. Here's what we call an anticline, a syncline, and then it just broke here. Weird. Okay, geologic structures are rock arrangements caused by earth movement. They relate to earth forces. They're produced by strain. Now, a strain is anything that'll change a shape. Here are types of stress and strain. The 3 basic types of stress are compressive, tensional, and shear. What's compressive? Squishing things together. Take some silly putty and squish it. What is tension? When you take the silly putty and you pull it apart. And what is shear? When you take a deck of cards and kind of swipe it to the side. Now those are forces. Strain is the change in size or shape in response to stress. I won't ask you a whole lot about strain, but I just wanted to put it in there. Again, here's compression, and it can cause folds. Here's tension, and it can cause lengthening or breaking. And here is shearing, and this can cause things that I'll show you in just a while. Now, rocks can behave elastically, like bending, as in this kind of stuff. They can misshape, or they can actually break. Now, can that really happen? Think of silly putty. If you pull it slowly, it deforms. If you pull it quickly, it snaps. Now, elastic materials normally return to their original shape after stress removal. Think of a plastic ruler. You can bend it, but it goes back to its normal shape. Silly putty, on the other hand, if you stretch it, does it go back to like it was? No. Now, there is something called the elastic limit. Just as we were talking about with the plastic ruler, you can bend it and it'll snap back until you reach the elastic limit. After you reach the elastic limit, it may snap, meaning it fractures, or it may do what's called ductile deformation, which means it just keeps its bend. I don't think that really happens with many plastic rulers. Now, this is important. If rocks are near the surface, they don't tend to fold. They tend to break. Why? Because nothing is constraining their motion. At depth, that's when we find rocks getting folded. These rocks, these have folds in them, which means They were, at the time when they were formed, far underground without these guys up here standing on them. Okay, so let's look at this. Were these rocks near the surface or far underground? We have folding, which means it must have been far underground, and then we have faulting, which tends to happen more close to the surface, but not always on the surface. Now, an important, have I said now a few times in here? Oh, gross. Geologists love things that are called outcrops. These are any areas where rocks are exposed to the surface. This is an outcrop. Now, in the movie that you're going to watch, you're going to learn about this. This is called the strike. This is called the dip. The direction of the strike in this case is north, and the angle of the dip is 30 degrees. In a real earth science class, you'll be looking at geologic maps and messing with this kind of stuff, but we're not going to do it here. What do you use to do that kind of thing? The movie talks about one kind of instrument. This is the more common kind of instrument. This is a Brunton compass. And you can buy one of these for only $206.83. This was off eBay. No, Amazon, I'm sorry. What's kind of crazy is you can get the Tilt Meter Pro, I think for 99 cents on your iPhone or other Android phone. This will do the same thing. I don't know. I just think it's kind of cool what's happening with smartphones. Now, what's going on here? This is a geologic map. What are all these little T's? They're showing you that the rocks are dipping down into the earth at an angle of about 30 degrees. And in this case, the strike is going north. If you were to walk along here, you'd be going across shale, and then across limestone, and then, across sandstone, and then across limestone. Ah, we have a key over here. That'll be handy. Here's a slightly more complicated thing. Here we have dips going that way at 25 degrees. We have dips going this way at 35 degrees. And you have several different types of rocks. You've got shale, which is the number 3. 2 is a red sandstone. 1 is a brown sandstone. Limestone is typically the brick formation, and conglomerate here. These are slightly different drawings than normal. But if you were to draw this in cross-section, this is what you'd be seeing. This is called an anticline fold. It looks like the letter A for anticline. The rocks have been squished together, and this layer that's in the middle is the oldest layer. What's happened? This was bent up and then down, and because this was bent up and down, it gets really weak in this area. If you've ever taken silly putty and bent it like this, you know that you get cracks right along here. In the same way that a glacier going over a ridge will create crevasses, this creates cracks, and these cracks tend to wear down really quickly. Okay, let's look at this outcrop. What's going on here? We've got folding, but instead of being up like this one, it goes down. This is called a syncline. Here is an anticline along a road cut, and geologists really do like roads because they expose a lot of rocks that we can look at. These are old sedimentary rocks that by now may be metamorphic due to all the pressure. And again, here you have an anticline and a syncline and a fault all in one. Now this goes into a little bit more depth than we really want to do, but here again is the anticline, here's the syncline. That's good enough for now. Now types of structures. This is out of, I believe, either Molly or Chad. I got this off of Google Maps. What are we looking at here? This is a satellite view looking straight down at something kind of like this. This area is from the Northern Rockies, where rocks have been folded up and back down. Wait, take it back. This is a syncline. This is kind of crazy. Here we are in the Appalachian Mountains, where North America has run into Africa, and all the rocks in here have been squished together, just like a towel on your tabletop. If you squish it together from left and right, it's going to get all these wrinkles in it. Folds. Again, this is a little bit more technical than we want to go, but let me cover a few things. A monocline is when you just have one bend. And again, where you get bending, you get a lot of erosion going on. An anticline is where you have an upward fold in the middle. A syncline is where you have a downward fold in the middle, and this is just a mess. These are overturned anticlines and synclines. Now once again, the highest part of an anticline tends to crack and it gets worn away first. This is a little bit weird. This is a little valley in Colorado where they're beginning to fracture for natural gas and go in for oil, and the water for some reason is not very good anymore. Now, a little bit more on folds. You can get, well, let's go into the big pictures. You can get these crazy folds. These are called isoclinal folds, but I don't want you to memorize that. It's not a big deal. You have overturned folds here. The pencil is there just for size reference. And in the Jura Mountains in Switzerland, you have recumbent folds where rocks are folded back on themselves. Again, this doesn't happen at the surface. This happens only at depth, and it takes millions of years for this to occur. Hey, take a look. Big recumbent fold, small recumbent fold. And there's just a pretty picture. Let's relax for a minute. Okay, let's keep going. Anticline. This is in Wyoming. This is Sheep Mountain. Kind of a beautiful area. Why don't we see anticlines more often? Here's an anticline. I forget. I think it's Sheep Mountain again. We're just looking the opposite direction. Take a look. There you go. In this case, we're looking from the north. Now, one of the things that helps create anticlines are domes. If you have something underneath a towel on your table and it rises up, let's say you put your dog under there and your dog stands up, you're going to create a dome out of the towel. And that can form an anticline. It's called a structural dome. You can also get a basin, which is kind of like an antidome. Here is a dome. And in this case, typically these are caused by a really low density material underneath, causing the sedimentary layers on top to arch over. You end up with these really weird erosion rings, and you can look underneath this for gas on top, oil on the bottom, and water underneath. Here's how big one structural dome can be. In the case of this dome, it appears to be about, I would say about 40 miles across and about 70 miles from top to bottom. These are the Black Hills in South Dakota. Here is another dome. Again, the part that was arched up is worn down really quickly. You have this really weird drainage in the middle, and then it's finally bisected, the rim, and the water escapes down this way. Here is a dome in Mauritania. Astronauts flying over this area noted. And here's a dome in northern Arizona. This is Lake Powell. This is Navajo Mountain, a big granite dome. In this case, it wasn't caused by oil or water or gas rising up. There was an igneous intrusion, granite being forced underneath layers of sedimentary rock, kind of like a zit under your layers of skin. You can also get a force uplifting rock, and it just creates a little pooch in the rock. Salt domes are a curious thing. Salt is less dense, and under pressure it flows, just like a glacier. And salt domes tend to rise underneath sedimentary rock. What do they cause then? Well, they bend the sedimentary rock, and they create places where water, oil, and gas rise, and they get trapped underneath impermeable rock like shale. I'm going to stop here, and we'll pick it up in part 2.